Alrighty. We're going to talk about electron configurations. This is going to tell us how uh, and where electrons are in atoms. Right? We've talked about orbitals and subshells and all that kind of stuff and quantum numbers, and this kind of brings everything together when we do that. Okay. Something we have to get at is, remember we talked about Stern and Gerlach's experiment with this electron spin, which defined our m sub s value being either plus a half or minus a half. What this led to is what's called the Pauli exclusion principle. And the Pauli exclusion principle tells us that no two electrons in the same atom can have the same force set of 4 quantum numbers, okay? So what this means is, if we're looking at this is a set of quantum numbers for a pair of electrons. Remember, N, L, and M sub L define for us the orbital, okay? M sub S is telling us the spin, okay? So what this tells us is in each orbital, we can have 2 electrons max, one that's spin up and one that's spin down. And when we put them in there together, we say that they are paired. So an up one and a down one will pair together, and their spins end up canceling out. And then towards the end of this, we're going to put that, come back to that and get into there. Okay. When we're talking about writing electron configurations, they look along the lines of this, right? Hydrogen would be 1s1. This is a 1s subshell that has 1 electron in it. Helium has 2 electrons. This is a 1s subshell with 2 electrons in it. Okay. Our goal in this is to figure out how to come up with these. Okay. When we're looking at this, if we're looking at a hydrogen atom, it's a little bit easier with only 1 electron in there. And when there's only 1 electron in there, all of the orbitals that have the same value of n have exactly the same value, have exactly the same energy, right? We say this is degenerate. Okay, they all have the same energy. Unfortunately, this is only true for hydrogen. So once you have more than 1 electron in your atom, the subshells spread apart, and each individual subshell has a slightly different energy in it. And you'll notice that in each set, as you progress down the list S, P, D, F, the subshells get higher in energy. So there's the 1s, here's a 2s, and then 2p is a little bit higher. Here's 3s, there's 3p, and 3d is a little bit higher. Here's 4s, here's 4p, and then 4d would be up here somewhere. Okay, and the pattern continues on. Okay, and there's some weirdness in here. We're going to go through that as we go. Okay, one of the things we got to watch out here when we're writing electron configurations is really there's 2 different, well, not really 2 different. There's one that we really care about, and that's the ground state. Ground state is the lowest energy electron configuration possible. This is typically what we're going for. This is our goal when we're writing the electron configuration. Okay, we're going to do this using the Aufbau principle, and I'm going to show you how to do that in a second. Okay, other electron configurations are excited states. So the difference between a ground state and excited state, the ground state follows the Aufbau principle. All of our principles and rules are followed, like the Pauli exclusion principle and other things that we're going to learn about in a second. Okay, an excited state is any allowed configuration that's not the ground state. And all we're saying here is that you have to not violate the Pauli exclusion principle, but they're violating something else, like the Aufbau principle or Hund's rule that we'll talk about in a minute. Okay. Typically, our goal here is coming up with the ground state. Eventually, we want to be able to recognize, are we dealing with a ground state or an excited state? And so we can talk about that as needed. Okay. So ultimately, when we're thinking about Aufbau, what we're going to do is we're going to prepare ourselves to put electrons in here. So our thinking is, right, we're going to put electrons in here one at a time. Okay, 1, 2. Each orbital member gets 2 electrons. So there's 1s2, and then go 2s2, and then we have 2p, which could have up to 6, and so on and so on. So, and there are ways through this. The point is you have to know what order the orbitals go in, okay, which they kind of almost go in order until you get to a certain point, because notice here 4s, 3d, 4p. You could brute force memorize all this. That's not the best way to do it. You could learn this weird diagonal diagram. This is one of the ways I learned to do this in high school, which, you know, in the dark ages. But, you know, this isn't too awesome either, because you have to memorize how to draw this diagram and then remember how it works. But essentially the order would be 1s and then 2s and then 2p 3s and then 3p 4s and then 3d 4p 5s, and it just goes on and on and on. Okay. This is not the best way either, because you have to remember this silly diagram. Okay. What we're going to do is we're going to use the periodic table, and the periodic table is set up in a way that's going to tell us what the electron configurations are. Okay. The table is broken down into blocks, and this is just how it's come about by how the periodic table is put together. The block tells you what the last electron subshell is going into. So these guys and helium are S blocks, so you're going to end on an S. The rest of the main group is P blocks, so you're going to end on a P. We have Ds in the middle. The transition metals are filling D orbitals, and then the inner transitions, those lanthanides and actinides, are filling F orbitals. And there's some weirdness in here, and we're going to talk about it as we do stuff, as we go. Okay. Where am I? Oh yeah. So something interesting to point out here is the lanthanides and actinides belong inside the D. Now I remember what I was going to say a second ago. Inside the D orbitals. So when you're filling stuff, and if you look stuff up, you'll see like it'll go 6s, 5d, 4f, 5d, 6p, and the f's will be inside the d's. We'll talk about that in a bit when we get into weirdness, but I'm not going to stress about it too terribly much. The other thing you want to pay attention to is the number of the period. So period 1, 2, 3, 4, 5, 6, 7 is equal to the value of n. Okay. And again, there's weirdness with D's and F's, and we'll do that as we work some examples here in a second. Okay. So our goal is, if we start with an empty atom, okay, and we fill it one electron at a time, and we count in the right order, we should be able to come up with what the ground state electron configuration is. Okay. All right, so let's do an example. This is the periodic table you'll have on exams. Where am I at? Okay, so let's do aluminum. So your first task is find aluminum. Aluminum is right here. Okay, I just wrote over the number I'm looking for. So aluminum is 13. So eventually when we're done with this, you need to account for 13 electrons. Okay. So when we do this, we're going to start at the beginning. So there's hydrogen. So that's 1s1. This is 1s2, and we're full because each orbital can only have 2. Then we have 2s1, 2s2, and we're out of 2s. We're going to come across over here, and now we have boron. So this is 2p. So 1, 2, 3, 4, 5, 6, and we're at the end of the row. So that's 2p6. Then we're in row 3. This is s, 3s1, 3s2, and now we're done with that. And then we're going to get here. Now this is 3p. We're at aluminum. So this 3p1, and we stop. Okay. Not too terrible. You don't have to put commas or spaces in there. I mean, you can put space if you want to. I just kind of string them all together. But you want to make sure that the number of electrons is a subscript, and you're using lowercase letters for subshells. Okay. All right, let's work another one. Mercury, Hg, purple. Okay, so gotta find Mercury. There he is, way down here. We're gonna do the same thing we just did. Okay, but we're gonna count from the beginning, and we're gonna go to Mercury. We should get to 80 electrons. Okay, so there's 1s1. I don't know if drawing the lines on here is gonna be helpful. 1s2. Eventually you get really good at doing this. Go faster the more you do. Okay, here's 2. We got 2s2. We're gonna come over here. There's this 2p. 1, 2, 3, 4, 5, 6. So that's 2p6. And you may get this 3s2, 3p, 1, 2, 3, 4, 5, 6. Okay, now we're down here. There's 4, s2. Okay, now we're going to pause. Okay, when you get here, we are now starting the transition metals and we're starting the Ds. This is where the Ds start, and the Ds start at level 3, but we're in period 4. So we have to remember here is when we hit Ds, we're going to turn this into n-1. Okay, so these are 3 Ds. Okay, we're going to counter all the way across. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we're full because there's 5 d orbitals, 2 electrons per orbital, and so on. Okay, now we're back over here. We're out of the D's, we're back into the P's, so we're back over here. This is N again. Okay, so this is 4. You can also remember we've already done 3p, so this should be 4p. We're going all the way across. 1, 2, 3, 4, 5, 6, 4p6. Then we're back over here. There's 5, S1, S2. Okay, then we're tagging in this d orbitals again, so we're at 4d this time. 1, 2, 3, 4, 5, 6, 7, 8, 9. 10. I counted somebody twice. There's 10 going across. Okay, 4d10. Then we're back up in the p's. Okay, we've done 4p, so this is 5p. 1, 2, 3, 4, 5, 6. Good. Okay, now we're 6s, 6s1, 6s2, and 6s2 is full. Now, officially what's happening here is if we're going in one at a time, the next electron ends up in 5d1 because lanthanum is next. Okay, but so all the D's get together. What we're going to do is we're going to jump, oh, excuse me, we're going to jump down here. Okay, this is n-2 because the first F's are 4. So really this is 4 and this is 5. Okay, so this is 4F. Okay, and there should be 14 of these because there's 7 F orbitals. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so 4F14. Then we're going to come back up over here to where lanthanum is, and we can count across our D10. This is 5D. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We got to mercury, so we're done. 5D10. Okay, this is a lot to write. If you count up all these electrons, there should be 80 electrons in there. Something to be of note here is that what we've done here is we've written the complete electron configuration. The complete electron configuration shows you every single electron in here. Okay, so it starts at the beginning and goes all the way to the end, which if you're doing something smaller towards the top of the periodic table, this isn't so bad. You're down here at mercury, this is a long dude to have to write out. Okay, we can abbreviate this down. I just have rewritten the same thing we just figured out, but now it's a legible typed one. If we think about what's going on here, so we looked at mercury here, okay, and if we think about it, everything from mercury starts at the same, right? All the atoms before mercury start the same way. 1s, blah, 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 2s, 2p, 3s, 3p, all the way down to xenon, okay? Then all of these atoms in this row, which includes these guys, look like xenon in the beginning, but then have a different number of other electrons. So we can abbreviate all of this, right? This business here is the same thing as xenon, okay? This is what we call the noble gas core. Okay, and everything after xenon has the same thing. Okay, everything after that is specific for mercury, right? If we wanted to say do iridium, that's 4 shorter than that, so that would end up 6s2, 4f14, 5d6. 10, 9, 8, 7, 5d7, I can't count, right? So that works. What's out here are the outermost electrons, and for most atoms, these are the valence electrons, and we're going to get into valence electrons in a second. For the case of mercury, those aren't all valence electrons, but we'll talk about that. I did so good except for right there. Okay. So this is what we call the noble gas electron configuration. Okay. You use brackets and put the last most recent noble gas. So if we were doing 10, we would start with krypton and then count from krypton to 10 for the rest of it. Okay. And so on and so on. What's I going at? Okay. The valence electrons are things that are outside of the core. And for most atoms, it's all the electrons outside the core. For some of them, it's not. Yeah, they're the highest energy electrons. They're responsible for the chemistry. So most of the time, we're concerned about valence electrons and not concerned about the core. When we're writing electron configurations, pay attention to the question, because they'll either say like, write the complete electron configuration, in which case you're writing all of this business, or write the noble gas electron configuration, in which case you're doing this shorter version. If it just says write the electron configuration, then you can do whatever your little heart desires and do it either way. Okay, whatever you feel like. Anyway, back to valence electrons. They're the outermost electrons. They're responsible for the chemistry. You can determine how many valence electrons are there by using the A or B group number system. This is why I stress the A-B group number system a lot. Okay, so group 1 has 1 valence electron. Remember, they all end S1. Group 2 has 2 valence electrons, that's S2. 3A, etc. to 8A have 8 valence electrons. Notice helium is going to have 2 because he only has 2 electrons. Transition metals, the B group numbers are weird, but the B group numbers tell you the valence electrons. So 3, 4, 5, 6, 7, 8, 8, 8, 1, 2. It doesn't make sense. We'll get into it later. Okay. The A and B group number is the number of valence electrons. Let's look at some more examples here. I'm going to do these as noble gas ones just because it's blanking on words, just because it'll take up less space. Okay. Fe is iron, which is here. The noble gas most previous to iron should be argon, which is over here. So we can start argon. Okay. And then we're down here. So that's 4s2. And then we're going to have 3d. Remember, we skipped that. 1, 2, 3, 4, 5, 6. 3d, 6. And we're done. Okay. We'll do tellurium real quick, and then I'm forgetting what comes next. Okay. Tellurium is over here. Its most recent noble gas is krypton, so we're going to start with krypton. Okay, and then we're down here at 5, so this is 5s2 because we did 1, 2. We're going all the way across the D's, so that's 4d10, and then we're going to tellurium 1, 2, 3, 4. That's 5p, p. Okay. Practice, 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 but the periodic table gives you the answer, so you just have to count. Okay. All right. Orbital diagram. Orbital diagram shows you a picture of the electron configuration. Okay. I've had students get confused about this before, and they draw an orbital diagram instead of writing the electron configuration. It's way too much work. Okay. The orbital diagram, this is the electron configuration. The orbital diagram is a picture that shows how the electrons are in there. Okay. How it's drawn, we've seen boxes, we've seen circles, whatever. I do it as lines because it's easier to draw lines. Okay, each line is an orbital, so that would be 1s. That would be 2s. And then there's 3 degenerate 2p. So all 3 of those are 2p. Okay. Our electron configuration tells us how to fill these in. Remember, each orbital pairs the electrons with a plus a half and a minus a half, so they're paired up. So 1s1, 1s2, 2s1, 2s2. Now we get to 2p, and you look here, there's 2 electrons, there's 3 orbitals, there's ways to do this. And it varies, okay? Well, it doesn't vary. There's one correct ground state and everything else will be an excited state, okay? The correct ground state way to do this is 1, 2, okay? This is using what's called Hund's rule. I think I have a pop-up about that in a sec. Let me just do it. Yeah, okay. Hund's rule says that you're filling degenerate orbitals one at a time with the same spin before pairing them up. So we're going to put one here and we're going to put one next to it. Okay, they can be both up or they can be both down. It doesn't matter as long as they're both going the same direction. Okay, notice we could have done, give you this another, right? There's lots of ways to do this. I'm just going to give us a couple more examples. These would be excited state configurations because they're not the ground state, but they are allowed, right? Because you could say something like that. You could pair them up, right? These are excited states and they violate Hund's rule. Okay, so when you're asking for a ground state orbital diagram, you want to follow Hund's rule. So that's one at a time before pairing them up, right? The reason there is there's a energy cost to pairing the electrons up, right? You're taking 2 negative charges and putting them in the same close vicinity to each other and they want to repel, okay? That's an energy cost, okay? So you put them a little bit farther away from each other and they don't have to deal with it. And then they're there, okay? Okay, let's do one for cobalt just so we can get an idea of Hund's rule for a bunch of stuff. And then we're wrapping this up. I'm sorry, this is becoming a long one. There's 1s, 2s, 3 degenerate 2p's, 3s, 3p, 4s. My little video square's in the way. Fun. Ah, shoot. Go back. Go back. Okay. 1, 2, 3, 4, 5. 3 Ds. All right, so we're doing cobalt. All right, so here's our electron configuration. We're just going to draw this as a picture, right? 1s2, 2s2, 2p6, 1, 2, 3. Hund's rule, pair them up, 4, 5, 6. Okay, 3s2, 1, 2. 3p6, 1, 2, 3, 4, 5, 6. Okay, 4s, 1, 2, and then 3d7. So 1, 2, 3, 4, 5. Then we compare them up, 6, 7. Okay. Hopefully not too terrible. Let me know if you have an issue. I'm gonna draw us a little bit of attention to, there's a lot of weird little, we treat them as exceptions, but they all have reasons behind them. Call these anomalous electron configurations, okay? And what's happening is we're going to focus on chromium and copper. In chromium and copper, right, the 3D and 4S are very close together. And for most transition metals, the 3D and the 4S are roughly the same, not exactly the same, roughly the same. And the atoms treat the 3D and the 4S as if they're all valence electrons together. Okay. Okay. What does this mean? That means what we're looking for here is atoms like to have a filled or a half-filled subshell. Okay, you can think of it that way. There's pairing energy costs and weirdness going on here. But let's look at the Ds. 1, 2, 3. Oops. Let me put a 4s over here. 4, 5, 3 Ds. Okay, so if we look at Let's do copper first because it's a little bit easier to grasp. Okay. Copper, we would expect to be 3. Why do I keep doing 3s first? This should be 4. We expect 4s2, whoosh, 3d9. Okay. In reality, this is 4s1, 3d10. Okay. The difference here is it promotes that electron to the 3d orbital because that's lower energy than the cost to pairing up electrons in the s orbital. So what we end up having is 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Because it would rather have a full D and one lone 4s than to leave it dangling with 9. The same kind of idea is true for the chromium bunch. 1, 1, 2, 3, 4, 5. So this is 4s, 3d. Okay, and if we look at chromium, chromium wants to be. You look at the rules and you're going to tell me it's 4s2, 3d4. Okay, but again, really what it's going to try to, what it wants to do, what it does is 4s1, 3d5, because it costs energy to pair the electrons up. So 1, 1, 2, 3, 4, 5. There, everybody is unpaired and there's no pairing cost. So you can think of this as a full shell and a half full shell, but really it's all about the cost of pairing electrons. Okay. These are the only ones I'm going to stress you to know about. There are a couple other things I'm going to point out in a second, but really focusing on the chromium group and the copper group because they all down the group do the same thing with this S and D stuff. Okay. Lactonides and actinides generally are kind of weird with their electron configurations because they all have this D, oops, I circled the wrong bit, this D electron stuff at the beginning where they're going to start 5d1 and then start doing 4f's, and then the F's are all close together, so they have weirdness. You can look those up and they're weird. I just want you to know why they're weird. They're all those subshells are really close in energy. And again, it's all about pairing costs. So drill this into your brain here. Pairing cost. Okay. To pairing those electrons up. Okay, I'm sorry, this is getting kind of long. One more. Okay. Magnetic properties. Remember, when we're talking about electrons, we use this word spin, right? Spin is an idea that leads us towards magnetism. Okay, this is kind of a physics idea here. If you have any sort of moving charge, will generate a magnetic field. Okay, so these electrons are sitting there and they're spinning around, and as they're spinning around, they're generating a magnetic field. So here we have one that's spinning up, and so it's generating an up magnetic field, right? So this might be plus 1/2, right? We draw it up. Here we have one spinning down, so this would be minus 1/2. We draw it pointing down. They all mean the same idea, but what you notice is their magnetic fields are going in opposite directions, okay? So when the two electrons actually come together and pair up in the orbital, their spins cancel out and there's no leftover magnetic field, okay? And this leads to the possibility of having magnetic properties for atoms. And we can characterize these things as either being diamagnetic or paramagnetic, depending on whether or not they interact with an external field. So what we want to think about then is if your atom or material or anything has unpaired electrons in it, has extra spin, it'll have a magnetic field and it will interact with another magnetic field. So if you think about it, your surface of your fridge is magnetic and you're sticking a magnet on it, they stick because the two magnetic fields want to interact with each other. Okay. If you have something that doesn't have a magnetic field and you try to stick it on stick it on the fridge, it's not going to work. It's going to fall off because there's no magnetic field to interact with. Okay. So things that are diamagnetic, and again, this terminology feels backwards. That happens a lot, and I'm sorry. But diamagnetic stuff has no leftover spin. All the electrons are paired. That's our key here. Diamagnetics are all paired up. In paramagnetic, you're going to have an interaction with a magnetic field. You're going to have leftover spin, and so you're going to have unpaired electrons. Okay, so we're going to come back to this a couple more times this semester, but what we want to be able to do is, can we recognize things that are diamagnetic versus paramagnetic based on how their spins are paired up? And for this, we have to be able to draw the orbital diagram. So we have to know Hund's rule, and we have to be able to tell, are there electrons that are paired up or unpaired as we do that? I don't know what did I just do? Shoot, I'm sorry. Okay, I just wanted to pop that up. Okay, so here, this would be a diamagnetic example because everything is paired up. In this one, this is a paramagnetic example because we have these guys that are unpaired. Okay. That's all I got, finally. Sorry, that was a long one. Let me know if you have questions, and I will see you later.